In this video, we're going to introduce the concept of a vector field. In the rest of the sections of this course, we're going to look at how the ideas and concepts of calculus apply to vector fields. So to start, we'll give the formal definition of a vector field. In very straightforward terms, a vector field is simply a function and we'll usually denote it, unless it has a special meaning, by capital F. And we are going to use the arrow notation because it is a function that outputs a vector. So it's a function f that assigns a vector to each element of its domain. In single variable calculus, the functions that you typically see have one real number as an input and one real number as an output. In this course, we've seen a couple of different types of functions. We've seen vector functions, which would have one real number input and a vector of 2 or 3 components output. We've seen multivariable functions where you'd have multiple variables input and one variable output. But this one is yet a different type of function. The input is either a point in a plane or a point in three-dimensional space, and the output is a vector corresponding to that point. Okay. So in terms of notation, we can think of this vector field. If we're doing a point xy in the plane, we could use capital F with the vector notation xy, and we need to know the two components of this vector. And so we'll often denote them by capital P and capital Q. And we'll think of these as functions of x and y. Of course, we could also use the ij notation if we preferred that. But notice that I am not putting arrows over the P and Q. It's because P and Q are not vector functions. They are just standard multivariable functions of two variables. Right? Very similarly, if we have a vector field in three-dimensional space, it's f of x, y, z. We're going to call the components p, q, and r. Again, these are not vector functions. And of course, we can use the ijk notation if we prefer the standard basis approach to writing vectors. And there will be, just like with regular vectors, there are times when each of these is preferred, depends on the context. Now these functions p, q, and r that are the component functions for our vector field, these are called scalar fields. So the way that we would typically represent a vector field pictorially is by taking either the plane or three-dimensional space in the region that we're defining the vector field on, and at each point drawing an arrow that represents the vector, capital F of xy or capital F of xyz, that starts at each point xy in that domain. Right? So in other words, if we have a vector field in the plane, at each point in the plane, we're going to have a vector starting at that point, and that vector is going to be the associated vector to the point, so capital F of xy. Now, of course, we can't draw an arrow at every single point, so typically we pick some representative points in our domain, and for practical purposes, that's what we use. We just draw some arrows with the appropriate direction and magnitude at each of those points. All right, so let's look at a simple example. So we will define a vector field in the plane. So this will be capital F of xy. And it will be given by the formula negative yi plus xj. And just to emphasize the notation here, we do have these two scalar fields. P of xy is going to, in this case, negative y, and q of xy is equal to x. Right, so when we use these scalar fields, we're just looking at the functions that are the components of our vector field. So if we want to draw this vector field graphically and represent it as vectors in the plane, the easiest way to do that is just to make a table of values. And so I'm going to make a table of a few points, x, y in the plane, and another column here for f of x, y, the associated vector. And we can make as many of these as we want in order to get a realistic picture of what's happening. I'm going to pick points around the origin. So I'm going to look at 0, 0. We can go out sort of to points that are 1 unit away. So 1, 0, 0, 1, negative 1, 0, 0, negative 1. So those are the 4 points where the unit circle hits the x-axis. And then we could go and do the same thing for maybe the circle of radius 2 centered at the origin. So we could look at 2, 0, 0, 2, negative 2, 0, and 0, negative 2. And at least for some representative purposes, this is good enough. And so the vectors here, we're just going to look at the first component being negative y and the second component being x. So this is quite easy to do. Right, so it'll look something like that. And then in our plane, right, the points we've just identified are these here. And so our picture is going to have an arrow from each of these points represented by the given vector that we just indicated. So at the origin, we're not going to have any vector drawn. It's the vector 0, 0, which is the 0 vector. At the point 1, 0, we have the vector 0, 1, which is going to point 1 unit upward. At the point 0, 1, we're going to have the point negative 1, 0, which points 1 unit to the left. At the point negative 1, 0, we have the the vector 0, negative 1, which points 1 unit down. And at the point 0, negative 1, we have the point 1, 0, which points 1 unit to the right. And so we've now indicated the first 5 vectors on our list. Notice the 0 vector we don't really recognize as a vector because we can't draw it in any tangible way. And then we move out to the points of 2 units away. So at the point 2, 0, we have the vector 0, 2, which points up 2 units. At the point 0, 2, we have the vector negative 2, 0, which points to the left 2. At the point negative 2, 0, we have the vector 0, negative 2, which points down 2. And at the point 0, negative 2, we have the vector 2, 0, which points to the right 2. And so we can see that at each point here, this graph is sort of pointing in the counterclockwise direction. And we if we look at the points along, like, say, a circle, the vectors are kind of continuously going around in that circle. So if we look at the 4 points I drew that are 1 unit from the origin, these vectors are all pointing counterclockwise 1 unit. And if we picked other points on the unit circle, we would see the same thing. It would be sort of a tangent vector to the circle of a length 1. Similarly, if we went out to the circle of radius 2, we'd see that these vectors are tangent counterclockwise to the circle and have a length of 2. So here's a computer-generated picture of what we were just looking at, and you can see there's more points in this picture than the one I hand drew, but you can see that at each given radius away from the origin, each given distance away from that origin, all of the vectors at that point, at that distance, sort of make a circular shape around. So what this is indicating is if we had some kind of an application dealing with a fluid flow or something like this, and we dropped some kind of a liquid into this plane, say around this point here, given this vector field, if this were the vector field that were in play by the forces in the system, the liquid would travel somehow around in this circular direction. It would follow these vectors around, and that's the main application of these things. Is that they apply to a lot of different areas in high level engineering, which of course we're not going to touch on, but that is sort of the one of the main uses of these things in practicality. So before we look at a couple other examples, we should point out that a vector field is said to be continuous if its component functions, the corresponding scalar fields, are continuous, and the vector field is differentiable if its component functions are differentiable. Now, it might look like we just use the words continuous and differentiable to define themselves, but notice that we're defining being continuous and differentiable for vector fields, and as its definition, using the fact that these scalar functions are continuous and differentiable, and we already know what that means in those contexts. Right? Now, the example we just saw, the vector function negative yx, is continuous and differentiable because it has scalar functions negative y and x, and both of those are continuous and differentiable. So let's take a look at another example. In this example, let's define a vector field f, again on the plane, using the following formula. We're going to take the vector xy, and we're going to scale it by a factor of 2 times the magnitude. Right, so we're going to look at this particular vector field. And so if we want to sort of understand what this does, we know that the first thing we should observe is that this is not defined at the origin, but it is defined everywhere else. If we allow the x and y to be the origin, we actually end up dividing by 2 times 0, which is 0. And so anything divided by 0 is undefined, and so we can't do that. But this is defined at every other point in the plane. The next thing that we can look at here is to find the length, the magnitude of the vectors at each point. And that's pretty easy to do. In this case, if I take this formula, f of xy, and I find the magnitude of this vector, right? This is just the magnitude of the vector xy divided by 2 times the magnitude of xy. All right, so we have just the scalar, 1 over 2 times the magnitude. All right, this is just a number. And we're going to multiply that by the magnitude of the vector xy. And notice that those simply cancel. We don't know, for each point, those are a different value. For each point xy, we get a different vector and a different magnitude, but they're going to cancel exactly. And so what we get is at each point a vector of magnitude 1/2. And we know that the direction of each of these vectors is just in the point xy. So f of xy is a vector that points radially outward, away from the origin at that point. And here we just saw that it has a magnitude of 1/2. So graphically, it will look something like this. So if at each point there's a vector pointing directly opposite of the origin and pointing outward 1/2 units. Right? So again, imagine all of these arrows being exactly the same length. It's hard to draw these things exactly perfect. But I think you can get the idea from this rough picture is that we're going to hit at every point a vector pointing away from the origin at that point, directly away at with a magnitude of 1/2. And here's a computer-generated image of the vector field in question here. And it looks roughly like what I drew, just of course more detail and more consistency in the length of the vectors. But at this point, this gives you exactly the idea of what will happen here. If we had a fluid flow given by this vector field, anywhere the fluid was dropped in the plane, the fluid would then start moving away from the origin at a constant rate of 1/2 units per time. Right, so before we move on, I will point out that our scalar functions, while are not directly given to us, are pretty quickly determined. P of xy here is going to be the function. In the numerator, we just have an x, and in the denominator, we're going to have 2 times the square root of x squared plus y squared. And our function q of xy will be the function y divided by 2 square root of x squared plus y squared. And of course, this first one I wrote for p should be x squared plus y squared, not x squared plus x squared. Right? And so we have these two scalar functions here that we get by actually computing the magnitude of the vector xy. And by looking at these, we see these are both continuous and differentiable everywhere they're defined. And the only point where they're not going to be defined is at the origin, which we saw the original vector field would not be defined at. So these two functions are continuous. These scalar fields are continuous and differentiable, and therefore so is our vector field f. So let's look at an example in three-dimensional space. So let's consider the vector field f of x, y, z given by the constant vector 0, 0, 1. Okay. And so this works exactly the same way at each point in 3 space. We have to draw a vector, and it's just more difficult to do here because we have to draw this at each point in 3-dimensional space, and it's harder to draw 3-dimensional objects than it is 2-dimensional. In this case, though, it's relatively simple. This vector is constant, so at each point in 3-dimensional space, we're going to have a vector that points in the positive z direction and is 1 unit long. And so should look something like this. So here we just picked a lot of arbitrary points in 3 space, but at each point the vector is pointing directly upward and is 1 unit long.